I wanted to make sure you all knew that you have a couple things for next time. So that's going to be the Canvas quiz on aromaticity, which will open up by the time you leave lecture today. It will remain open until Monday's lecture time, so Monday at 11:30. So sometime between the end of class today and the start of Monday's class, just make sure to get onto Canvas, go under quizzes, and you'll see that there's only one available to you. It's called Aromaticity Quiz, and you can take that. The other thing that you're going to have due, which we'll cover today, is your aromatic nomenclature homework. So this is just practicing with how to name aromatic compounds. The homework is, I think, about 8 aromatic molecules that you need to come up with the IUPAC name for. This will also be due at the start of class on Monday, and you can just upload this to Canvas. Okay? Any questions about the assignments coming up? Okay, so I think what I'm going to do today, I teach in here for all of my lectures in this class, and I really am a bit dissatisfied with the lighting and the way things appear on the board. I think there's, number one, it's kind of dark, and number two, there's a kind of a significant glare on the board, and I think it's hard for some people to see. And so what I tried last night in my lecture was using my iPad, and it just appears a lot brighter, and I think it's going to be easier for y'all to see it that way. So I'm going to try that out with y'all, and if you like it, then great, and if you don't, just let me know, and I can go back to the whiteboard. It really makes no difference to me. The only drawback of using the iPad to lecture is I'm going to be kind of tethered to the desk, and I don't particularly like that, but I don't know if it probably doesn't make a difference to y'all. But in any case, I'm going to start off trying this with the iPad. If you don't like it, just let me know, and I can go back to writing on the whiteboard. Okay? Okay, so let's go ahead and pick up where we left off. So if you remember back from Monday, what we had started talking about was how these concepts of aromaticity will affect ultimately the reactivity of species. So we saw a couple of different examples of this. We looked at, for instance, cyclopentadiene. And then we kind of compared that to a similar allylic system, cyclohexene. And we said that there was a very large difference in the reactivity of these two molecules, right? And specifically the acidity of those two molecules. So for instance, we had said that the acidity of these protons was very, very high, so high it's actually difficult to measure accurately, somewhere between 45 and 50, whereas the acidity of those hydrogens was approximately 16, right? So a vast, vast difference in acidity for seemingly very similar protons. So why was that? Well, if you take a look at where you're starting from and compare it to where you end up, it really tells you everything you need to know. So if I deprotonate the cyclopentadiene, I get something like that. And the significance here is that you're starting with something that is non-aromatic. Does that make sense? Can everybody see that? Does everybody understand why cyclopentadiene is considered non-aromatic? Whenever you're trying to determine aromaticity of anything, we have to go through the 4 criteria. And if you look at cyclopentadiene, that carbon is sp3 hybridized. And one of the criterion, obviously, for aromaticity is that everything has to be sp2 hybridized. So the fact that this fails that second criterion makes this a non-aromatic compound. Now let's go over to the product side. If we go over to the product side, does everybody remember what we talked about here? That lone pair containing carbon would be sp2 hybridized. Right. It's a little bit unusual, right? Because in Gen Chem, you learned that something of this bonding style should be sp3 hybridized and trigonal pyramidal like ammonia. However, the exception to that is when you have these lone pair containing atoms adjacent to a pi bond, they are sp2. Okay? So, knowing now that this atom is sp2 hybridized, we can go through those 4 criteria. Trigonal with conjugated pi, cyclical with conjugated pi bonds, yes. Everything's sp2, yes. Flat and planar, yes. And then in terms of pi electrons, you got 2, 4, 6 pi electrons. This satisfies all 4 criteria, and this is an aromatic ion. And so this is something you're going to see, and we looked at another couple examples, I think, last time, but situations where you're going from something that's non-aromatic to aromatic will tend to happen very, very readily, because the aromaticity is such a favorable energetic state to be in. However, if you go to the opposite scenario, say take something that is aromatic or even non-aromatic and trying to make it anti is going to be virtually impossible. And we saw that with the example of the alcohol. If you try to treat this with acid, frosinate the hydroxyl, make it leave, what we're trying to do there is make that cation. Because this cation has only 2 4 pi electrons, this would be an anti-aromatic cation. And as a result, this reaction is virtually impossible to do. Okay? So in this case, you're starting non-aromatic and we're ending anti, and that is very, very difficult to achieve. All right? Any questions on this idea? Okay, then let's go ahead and move. So far, when we've been looking at these aromaticity concepts, we've been focusing in on carbocycles, meaning cyclic compounds of carbon. And we can extend that to heterocycles as well. So let's look at one of the more common heterocycles. So whenever I say a heterocycle, we're just talking about a ring that contains a hetero atom. Right? So something like this. Now when you get into heterocycles like this, the trick here, I mean, we can go through the criteria. Cyclic with conjugated pi bonds, yes. Everything's sp2, yes. Planar, we can assume. The question is, how many pi electrons? So we clearly have 2, 4, 6 from the pi bonds. But the real question is, what about the lone pair? And that makes a very big difference. Right? If this lone pair is part of the pi system, then you're going to have 2, 4, 6, 8 pi electrons, and it would be anti-aromatic. However, if this is not part of the pi system, you have 2, 4, 6 pi electrons, and it is aromatic. So the trick to handling these heterocycles is to figure out what is the disposition of the lone pair. Is it part of the pi system? Is it not part of the pi system? And so that's what we're going to focus on right now, is figuring out how do we determine whether a lone pair is or is not part of the pi system. So, I don't know. Sorry about that. Okay, but anyway, what we're going to try to do is figure out what's happening with the lone pair electrons. So if we look at the nitrogen, can you see how this would have to be an sp2 hybridized atom? Right, an atom that's making one pi bond. So anything that makes one pi bond has to be sp2 hybridized. And if we can agree on that, then what that means is in terms of the places it has to put electrons, it has 3 sp2 hybrid orbitals and 1 unhybridized p orbital. All right? So let's just go through and see if we can figure out what the nitrogen is doing with each of these orbitals. So, nitrogen is making a sigma bond to carbon there. Well, sigma bonds can only be made with hybrid orbitals. So, one of them is used for that sigma bond. It's making another sigma bond to that carbon. Again, sigma bonds can only be made with hybrid orbitals, so that takes up a second. It's making a pi bond also to that carbon. Well, pi bonds can only be made with p orbitals. So the pi bond is taking up that one. Well, that only leaves one more spot. So that tells us that the lone pair in this case has to be occupying that remaining orbital.
How do we know it's not like the carbon above it where it would be like sp hybridized and have 2p orbitals?
It doesn't have 2p orbitals. If it had 2p orbitals, it would be sp hybridized.
Right, why couldn't it be sp hybridized?
Because this is only making one pi bond.
Yeah, but what if the electrons were in a p orbital? Like, why couldn't it have 2p orbitals? Like the carbon above it where you...
That carbon only has one.
Are we talking about the nitrogen or the carbon?
We're talking about the nitrogen. Because the nitrogen is the one holding the lone pair. So that's the one we're concerned with. We want to see where is the nitrogen putting the lone pair. Is it putting it in a hybrid orbital or is it putting it in a p orbital? Because if it's putting it in a p orbital, it's going to be part of the pi system.
I guess I just don't understand why it couldn't be sp hybridized and have 2p orbitals and put the electron in one of the p orbitals. How do we know that's not happening?
Because if it was sp hybridized, it would have a triple bond. And it would be linear in bond angle. There's no way you can have something with a single pi bond and have it be sp hybridized.
Okay.
So what we're looking at here then, in terms of the number of pi electrons, this is showing us that the lone pair of the nitrogen is not in a p orbital, and therefore is not part of the pi system. So in terms of how many pi electrons do you have, you've got the 2, the 4, the 6. 6 pi electrons, and so this compound, this is pyridine by the way, 6 pi electrons, and thus it satisfies all criteria for aromaticity, and thus is an aromatic heterocycle. Let's do another example. Let's look at a very similar compound. Let's look at this one. Okay, so this one is called pyrrole. Does it make sense to you that this nitrogen would also have to be sp2 hybridized? So yeah, this kind of goes back to what we were talking about a little bit earlier. I mean, if you were to ask a Gen Chem student this, they would say it's sp3 in trigonal pyramidal because it has the same bonding pattern as ammonia. 3 bonding groups and a lone pair. However, this is a lone pair atom adjacent to a pi bond. And anytime you have that, the lone pair atom will be sp2 hybridized in order to delocalize the electrons through the ring. All right? So if that nitrogen is sp2 hybridized, then like the previous example, that nitrogen is going to have 3 sp2 hybrids and an unhybridized P. So we can go through the same process that we went through earlier. This nitrogen is making a sigma bond to that carbon. That takes up a hybrid. It's making a sigma bond to the other carbon. That takes up a hybrid. And it's making a third sigma bond to hydrogen, which takes up a third hybrid. So the only place we have left to put the lone pair in this case is the P. It's in a P orbital, and thus it participates in the pi system. So when we go to count pi electrons in pyrrole, you've got the 2 of the lone pair, the 4 of the pi bond, the 6 of the pi bond. And so this gives us a total of, like purine, 6 pi electrons, and thus pyrrole is aromatic as well. Does anybody have questions on that? And so, as I said a few times before, this has significant consequences on the reactivity of these things. So let me give you some numbers, and then we can see if we can figure out where they come from. So I'm going to give you some pKb numbers. So just as a quick reminder, pKb is a measure of base strength. In the same way that we can use pKa to measure the strength of an acid, pKb is what's used to measure the strength of a base. And just like pKa, whereas the lower the pKa, the stronger the acid, well, same analogy holds for bases. The lower the pKb, the stronger the base. So pyridine, it turns out, has a pKb of about 8.75. Pyrrole is significantly less basic at about 13.6. So what would be the rationale, what would be the reason for this significant difference in base strength of these two seemingly very similar compounds? Well, let's have a look. Let's see what they look like when they both act as a base, when they both grab a proton. So pyridine looks like this in its neutral state. If you protonate it, it looks like that. Pyrrole, it's like that in its neutral state. If you protonate it, it looks like that. So we've already established that both of these heterocycles are aromatic in their neutral form. So let's look at them once they protonate. The pyridinium ion. Cyclic with conjugated pi bonds, yes. Everything is still sp2 hybridized, yes. Planar, we can assume so. How many pi electrons do we now have? Well, 2, 4, 6. It still meets all criteria for aromaticity. So it doesn't matter whether it's neutral or whether it's protonated, it's aromatic either way. So protonating the nitrogen and pyridine does nothing to affect the aromaticity of the molecule. What about pyrrole? What do we think about this one?
Is it anti?
Close. I mean, you're right. It loses a pair of electrons as it protonates, so it has 4 pi electrons, but does it satisfy everything else? Yeah, this guy's no longer sp2 hybridized, right? The nitrogen now has 4 bonds, and thus is sp3 hybridized. So because that becomes sp3, it's not going to be anti-aromatic, but it is going to be non-aromatic. And again, that's not going to be a favorable process. Anytime you're taking something that's aromatic and doing something chemically to it to make it non, or worse, anti-aromatic, that is not going to be a favorable process. And you can see that directly reflected in the strength of these 2 bases. The pyrrole, as a result, is a much weaker base than the pyridine. Does anybody have questions on these? So let's look maybe at, I want to do 2 more with you just to make sure we have a good handle on this. So let's look at a slightly different heterocycle, because we can do things other than just nitrogens. We can substitute virtually any atom with lone pair electrons in these. All right, so let's do this one. So that's oxazole. And obviously it has 2 heteroatoms in the ring. So what you need to do, I'll give you a minute to figure this out, is you need to figure out where these 3 lone pairs of electrons are going. Are they in p orbitals? Are they in hybrid orbitals? Because again, it makes a big difference. If they are in p orbitals, if any of these are in p orbitals, they will contribute to the pi system. So take just a minute and see if you can figure out what's going on with those lone pairs. So first off, can we all agree that both of the heteroatoms are going to be sp2 hybridized? Does that make sense? The nitrogen has to be sp2 because it's making a single pi bond. Anything that's making one pi bond is going to be sp2 hybridized. The oxygen has to be sp2 hybridized as well because it is a lone pair containing atom adjacent to a pi bond. Actually adjacent to 2 pi bonds, but still. So both of these atoms are going to be sp2 hybridized, and that means both of them have the same number and types of orbitals available. So the nitrogen is going to have 3 sp2 and a p, and the oxygen is also going to have 3 sp2 and a p. So let's deal with nitrogen first. The nitrogen is making a pi bond to carbon, so that's going to occupy the p orbital. Then it's making a sigma bond to carbon. That'll take up one of the hybrids. It's making another sigma bond to carbon, occupying a second hybrid. That leaves the only place left to put the lone pair in the hybrid. So what that tells us is that nitrogen lone pair is not part of the pi system. All right, what about the oxygen? The oxygen is making a sigma bond to carbon, occupying a hybrid, a second sigma bond to carbon, occupying a hybrid. What that does for us is it tells us we still got 2 lone pairs in place. So one lone pair gets the hybrid, and one lone pair gets the p. So when counting up pi electrons, then you got the 2, 4 of the pi bonds, and then 1 of the oxygen lone pair, for a total of 6. 6 pi electrons, aromatic heterocycle. Does anybody have questions on this? Yeah.
Can you explain again how you got 6?
Yeah, because you've got the 2 of the 4, right, the pi bonds, those are going to count for the pi system, obviously. The only lone pair that's going to count in terms of the pi system here, these don't, because they're not in a p orbital. These don't, because they're not in a p orbital either. The only lone pair that's going to count towards the pi system are going to be these guys, because they're in that p orbital. So, in terms of pi electrons, you've got the 2, 4 from the pi bonds, and 1 of the oxygen lone pair, for a total of 6. Any other questions on this? I do want to show you just quickly, sometimes a picture helps to show how these things work. I want to look at, here we go. This is the molecular orbital view of both pyridine and pyrrole that we discussed a second ago. So if you look, you can see that there's the pi system of pyridine, and it's carrying that lone pair of electrons that it has in that hybrid orbital. And you can see that because of the geometry of the hybrid orbitals being 120 degrees apart from one another, it is not part of that pi system. The lone pair of electrons are in the plane of the ring. They're 90 degrees apart from the pi system. And so when this protonates, it's using this lone pair to grab the proton. So it is, by protonating, you're not doing anything to disrupt the pi system of the ring, which is a very different scenario from pyrrole. Pyrrole is carrying the nitrogen lone pair in the pi system. so that when pyrrole grabs a proton, it has to use one of the pi system lone pairs to go and grab that. So you can see by protonating this guy, it has disrupted the pi system of the ring and takes this from being an aromatic neutral compound to a non-aromatic ion. Okay. Does anybody have questions on this? All right, let's look at one last one. We'll put this to bed. For anybody that's had biology recently, you may recognize this one. So this is thymine. This is one of the nucleic bases found in DNA. So take a minute and see what you can do with this. Tell me if it's aromatic, anti, or non-aromatic. So does it make sense looking at these nitrogens that they would both be sp2 hybridized? Right. Because they're both lone pair containing atoms that are adjacent to a pi bond. Lone pair containing atom adjacent to a pi bond. So both of the nitrogens are going to be sp2. And they really have identical bonding styles, if you think about it. They're both making 3 sigma bonds, and they have a lone pair. So each of the nitrogens are sp2. They're each making 3 sigma bonds, which occupy the hybrid orbitals. And that leaves only one place to put the lone pair on each of them. Both of them have their lone pair in the p orbital, which makes them part of the pi system. So when you go to count these, you've got 2 pi electrons from the pi bond, and then both of those nitrogen lone pairs count for a total of 6 pi electrons, making it an aromatic species. Okay. Any questions on this before we move on?
I was a little confused with like the double bond
these don't count, because they're not in the ring, right? They're kind of pushing outside of the ring, so they do not count towards the aromaticity of the ring. It's only things that are directly inside the ring. Okay, so, you know, sometimes when you're learning about these things, it's like, who really cares? This stuff was figured out hundreds of years ago. Why am I being tortured with this now? I want to show you, people are still looking into this stuff. So back about 5 years ago or so, a group out of Japan synthesized at the time, 2015 or so, it was the largest aromatic molecule ever known, which is right here. And so it's a series of pyrrole rings. And the thing is, as it is right now in its neutral state, actually has 52 pi electrons, which if you do the math on that, that's actually an anti-Huckel number. So in its neutral state, it's not anti-aromatic because it's such a large ring, it has a lot of flexibility, and so it kind of bends out of planarity, adopts a non-planar conformation, and is just a non-aromatic ring. However, if you treat it with a little bit of acid, one of those nitrogens protonates, and it takes it from 52 pi electrons to 50 pi electrons, which is a Huckel number. It flattens out and makes it the largest heterocycle known. So it's pretty interesting how these maybe theoretically abstract ideas have real world effects on molecules. Now, not to be outdone, back about 2 years ago, a group out of Britain said, I'm going to do you one better, and created the current world record holder for the largest aromatic compound. So it's really quite pretty. Really has no function in the real world, but it's what we call theoretical organic chemistry, or sometimes physical organic chemistry. These people build these molecules to kind of push the boundaries of the theory. Yeah, so there you have it. About 2020 they did this. Okay, so that's pretty much the end of aromaticity. So what I would like to do is let's switch gears a little bit and get into the third and final chapter of the unit, and we'll look at the benzene reactions. So, by the way, is the iPad thing working for y'all? Is that okay?
It's fine.
Okay. So let's go ahead and all right, so before we get into the actual reactions of benzene, what we're going to do is spend a little bit of time on how to name these aromatic compounds. All right, so let's tackle a little bit of nomenclature first, and then we'll get into the chemistry of these things. So if you have a mono-substituted benzene ring, it's very, very simple to name them. Actually, the nomenclature of all of these aromatic compounds is quite easy, especially in comparison to the nomenclature you've been subjected to so far. But if you have a mono-substituted benzene ring, all you have to do is give the name of the substituent followed by benzene. So I can see I've got the 2-carbon substituent here, obviously an ethyl group, so I just say ethyl benzene, no space, all one word. Similarly, if you have the chlorine on the ring, that makes it a chloro substituent, chlorobenzene, all one word. And then finally, you've got this group, which is the nitro group, nitrobenzene, all one word. Okay? Give the name of the substituent, followed by benzene, and you're done. All right? Now, when you start putting more than one substituent, we have to give some idea of where these substituents are relative to one another, right? So, for di-substituted benzenes, oh, actually, before we do that, you do need to know some of the common names. Some of these guys have been around for so long that they have common non-IUPAC names associated with them. And you probably know a lot of them already, right? So, you know, if you put an OH group on benzene, we call it a phenol. Nobody says methylbenzene, everybody just calls that toluene. If you've got the NH2 group, that's an aniline compound. The methyl ether is what we call anisole. And then down here, with the vinylic substituent, we call that styrene. You've probably heard of the term polystyrenes, used in plastics. With the ketone, we call that acetophenone. The aldehyde, benzaldehyde, and the carboxylic acid, benzoic acid. So these are just ones you need to commit to memory. And I'm going to give you one more, and it is isopropylbenzene. So people refer to this by its common name, which is cumene. All right? So you just have to commit them to memory, and like I said, I'm sure you probably know most of these already. But all right, so let's move into the di-substituted compounds. Everybody get a chance to write those down. Okay. So with the di-substituted, what we need to do is identify kind of the base. Meaning, if there's a substituent on these that gives it one of its common names, then you're going to call it that. Okay, so for instance, if I'm looking at this guy, the hydroxy substituent here makes this a phenol ring. So I'm going to call it some kind of a phenol. But it's not just regular phenol, because I have to indicate that there's a bromine on it too. So I have two choices. I'm going to call it bromophenol. But I have to indicate in the name where on the ring the bromine and the hydroxyl are relative to one another. And so you can do this kind of in an IUPAC way, which would use the numbers, right? Because I'm calling it a phenol, I'm going to assume the hydroxy is at the 1 position. And then if you were, follow the normal rules for rings, you number around so that the other one would have the lowest number possible. So I could call this 3-bromophenol, and that would be perfectly correct. But did y'all learn last semester about this ortho-meta-para stuff? Does that look familiar? Okay, so with these di-substituted benzenes, you can also use this style. And you see it a lot. But if you've got two substituents and they're right next door to each other, you can call those ortho. So you just put that kind of out in front of the name. If they're 1 carbon removed, if they're 1,3 to each other, you can call that meta. And if they're on opposite sides of the ring, 1,4 di-substituted, we call that para. And a lot of times you'll see it's just an abbreviation with the letter out in front. So I would be perfectly correct to call this ring 3-bromophenol. I could also, if I wanted to, just put an O in parentheses. So for, oh sorry, no, that's a meta. An M in parentheses, bromophenol. So whichever one you prefer, both are perfectly correct. Right. Let's go over to this guy. Is there something on this ring that would make it a common name? What's that? To this one, sorry. Yeah, the NH2 would make that an aniline compound. So we're going to call it something aniline. And if you look right next door, it has that 3-carbon alkyl group, which would be a propyl. And the last thing I need to do is give how they're related to each other, right? So you could either call this a 2-propyl aniline, that would be perfectly correct, or if you wanted to use the orthometapara, I could say orthopropyl aniline. Let's look at the next one over. This one throws a little wrench in the system here. If I'm looking at this one on the left, do either of those substituents give it a common name? Yeah, the hydroxy would make this a phenol. What about this? That ketone would also make it a common name. The ketone would make it an acetophenone. So what do? Are we going to call it a phenol, or are we going to call it an acetophenone? When you have a choice like that, you're going to follow the priority rules. All right? So the ketone, well, any carbonyl functional group has priority over anything that's non-carbonyl. So the acetophenone in this case would have priority over the alcohol. So because of that, I'm going to call it an acetophenone. And that's just going to have the OH as a substituent. So I would say it's a hydroxy acetophenone. And just like in the previous ones, you could either give numbers to indicate positions, so 4-hydroxyacetophenone, or if you prefer, just put P out in front, hydroxyacetophenone. Any questions on these so far?
So on the one that you did, has the phenol and the neon, why does it go like the direction? For those ones that keep shouldn't it be going the other way? Because it needs to.
Well, so remember, the rules for rings is you want your substituents to have the lowest possible numbers. So if I number the way I did, I get a 1 and a 3 substitution. If I numbered the other way around, you get 1, 2, you get 1, 5. So you want to keep your numbers as small as possible.
So I guess, so the numbering overrides, like, because the direction that it's supposed to go, is it supposed to be the bottom, like, it's supposed to cover the whole alpine?
No, it doesn't really matter. You just want the numbers to be as small as possible. And so a 1-3 situation is going to be a lot better than a 1-5 situation.
I think he's wondering about the double bonds, but remember they're really a resonance structure where the whole thing is double bonded.
Yeah, and the fact that we're calling it a phenol tells you that you're dealing with a benzene ring. It's not like we're dealing with a 1,3,5 cyclohexatriene or something like that, right? We're putting this in an entirely different functional group class. So it's not handled like the cycloalkenes, for instance, because it's not a cycloalkene, it's actually a benzene compound. It's an aromatic compound. It's a different class of functional group. Okay, so I want to look at this last one because it illustrates a point. This one here is our primary ring, and it's got that methoxy group. And so the presence of the methoxy makes that a common name, which we call anisole. And if we do that, what that means for us is that we have this benzene ring, that's our primary one, that has another benzene ring as a substituent. And so I'm not sure, you may not have seen this before, but when you have situations like that, if the benzene is present as a substituent, it would make sense to call it a benzyl group, but of course, we're not gonna do that, because that would just be too logical. A benzyl group is something else. When you have these guys as a substituent, we're gonna call it a phenyl group. So it would be phenyl anisole. And again, if you want, you can use the numbers, which would be 3-phenyl anisole, or if you prefer, meta phenyl anisole. All right. Any questions on these? All right, so the last kind of step of the nomenclature story is what happens if you have more than 2 substituents. If you've got more than 2 substituents, you're forced to use the numeric. You can no longer use ortho meta para when you have more than 2 groups. So let's look at a couple examples of that. So let's look at this guy here. So looking at this structure, does any of these substituents give it a common name in this one? This one? Yeah, exactly. You've got this carboxylic acid group on the ring, which makes it a benzoic acid. So that means that is going to be our number 1 position. All right, the one that's giving the name of the ring is always the 1 position. So numbering around, we have a choice. You can go clockwise or counterclockwise. If I go clockwise, we get substituents at the 1, 3, 5. If I go counterclockwise, I get substituents at 1, 3, 5. How do we break that tie? Was it?
Alphabetical?
Yep, exactly, alphabet. We get 1 through, the same numbers regardless of how we number around the ring. And so in a case like that, you go alphabetically. The bromo comes before the nitro, and so I'm going to number around clockwise. So then we alphabetize the substituents. Yeah?
Could it also be a nitrobenzene or no?
No, nitrobenzene is not one of the common names. So, I mean, that's how you would call it as a monosubstituted derivative. It would be nitrobenzene, but it's not a common name like an anisole is for methoxybenzene. You know, nitrobenzene is just saying I've got a nitro on the benzene ring. It's just a normal monosubstituted name. Okay, so this one would end up being then what? 3 bromo 5 nitrobenzoic acid. All right. And look at the last. Let's look at this last one here. We're looking at this guy. I think the only thing on here that's going to make it a common name would be the NH2, would make it an aniline compound. That means we start numbering there. That's the 1 position. And in this one, I think it's pretty apparent the way we're going to have to number around. This one, we're going to want to go counterclockwise to give us the smallest numbers. So then this would become 2-chloro 4-ethyl aniline. Okay. Any questions on the aromatic nomenclature? So that's what your homework is going to be like. This is going to be a series of, I think, 8 different benzene type compounds that you need to come up with the names for, just like we've been doing with these. All right.
Professor, so for the first example, what was the parent, base?
Oh, it's a benzoic acid. So this carboxyl group here makes the whole ring system a benzoic acid compound.
Is there something in Canvas to list like the benzoic acids and the anilines and those, so that we know which thing is called what?
Like the priority? Or?
No, just what the names of them are.
Oh, the ones that you need to know are the ones on the slide.
Okay.
Yeah, those are the ones you need to know.
Okay.
Okay. Any other questions on nomenclature before we move on from that? Yeah. I'm sorry, say it one more time. Yeah, if you look on Canvas, there's in the Unit 1 module, there's a functional group priority list there that kind of just, for nomenclature purposes, so it just kind of lists the highest priority functional group all the way down to alkane in order. So it's on Canvas. Okay, so let's go ahead and move on and look at some reactivity here.
Can you read the last one?
Oh, the last one? Okay, so with this one, it's going to be a lot easier to name this as a straight chain instead of naming it as a benzene. So what I would probably do in this case is number the parent here like 1, 2, 3, 4, 5, 6, 7. Because the parent then is going to be an alkyne compound. And so if we're saying that the parent is an alkyne, that means we want it to have the triple bond to have the lowest number possible. So this is just going to end up being a straight chain alkyne with a phenyl substituent. So we would end up, just like normal, arranging the substituents alphabetically. So that would be what, 5-bromo, 4-methyl, 7-phenyl, hept, 2-ine. Okay.
Thank you.
Do alkynes take precedence over benzene rings in that list, or just because of the size and choose?
When you have double bonds and triple bonds, they're, for practical purposes, about equal priority. There are, if you look at the list, alkenes technically have priority over alkynes, but that's in very specific situations. So generally speaking, the double bonds and the triple bonds have about equal priority. Like if you go back to the example we looked at back at the beginning of the semester, we saw some enine compounds, and it didn't matter whether the double bond was closer to the end or the triple bond was closer to the end. You handle them all as just multiple bonds, numbering so that closest to the end of any multiple bond, regardless of whether that was triple or double. Okay, so for most purposes, double bonds and triple bonds have about equal priority.
And in this case, we just chose that direction because it's easier to name.
Yeah, we chose to name it as an alkyne instead of as a benzene ring because, yeah, I mean, that would be really tedious to name that as a complex constituent. It's a whole lot easier to name this thing with a phenyl group than this thing with that kind of group, right? Okay, so then let's go on to the reactions of benzene. So we went through last chapter, and I told you how, in a relative sense, how unreactive benzene was. And I didn't mean to give you the impression that benzene just doesn't do reactions. Benzene does reactions, just not the normal kind of reactions, right? So let's take a look at that and see why that would be. You know, you looked a lot last semester about taking alkenes and say, adding a halogen across them. Right? And if benzene were to do this reaction in the same way that the rest of the alkenes do, what you would get is something like this. So why is it that benzene does not do this reaction like the rest of the alkenes?
Because that's less energetically favorable than that.
What'd you say, Denise? Sorry?
That would be less energetically favorable
Yeah, why?
than that. Because that's aromatic and that's non-aromatic.
Yeah, exactly. If benzene were to react in those normal addition style mechanisms, you're taking an aromatic species and breaking it down into something that's non-aromatic. And as we've seen before, that is really, really unlikely. And so what that means for us is if we're going to try to make benzene do chemistry, we're going to have to do it in a way that allows benzene to retain its aromaticity. All right? We're not going to be able to take aromatic and go to non-aromatic. We're going to have to start aromatic and end in aromatic. And so all of the reactions that almost all the reactions we're going to see in this chapter are going to fall under a new mechanistic manifold, something we haven't seen before, and it's what we call electrophilic aromatic substitution. A lot of times you'll just see this abbreviated EAS. So what I'm going to do is I'm going to show you kind of a generic mechanism, and then we'll look at some specific reactions you can do with it. All right? So all of these reactions are going to kind of follow this same generic mechanism. And you're going to start with the benzene. And in the first step, we're going to have pi electrons go and attack an electrophile. Now, if you think about that, we're temporarily doing something I told you we couldn't do. You know, if you have the pi electrons of benzene go and grab an electrophile, it's going to temporarily disrupt the aromaticity of the system. And because of that, these are not going to be your mother's electrophiles. These aren't going to be the normal run-of-the-mill electrophiles that you've been dealing with up to this point. These are going to have to be extreme electrophiles. So reactive that you can't even buy a bottle of them. Like you can't buy a bottle of these types of electrophiles, store it, and then use it as you want. Because they're just too reactive. They don't hang around. So with all of these reactions, what we're going to be doing is we're going to be combining a couple of things, which is going to make this super hot electrophile that's going to get consumed as soon as it's formed, because it's just that reactive. Right? So, but in this, we'll look at some specifics in a minute, but we have this super hot electrophile that's starved for electrons. It's looking for electrons wherever it can get it. It sees this electron-rich benzene ring, and so that's what's going to react. We're going to coax those pi electrons out of the ring to attack. That's going to make this high energy intermediate what we will refer to from here on out as our sigma complex. If you read older textbooks, sometimes they call this an arenium ion. And then in the next stage, so think about this from kind of like an energy diagram. We started really low because benzene is very happy in its aromatic state. We go really high to the sigma complex because you've taken something that's aromatic and made it non-aromatic. And then in the next stage, we are going to restore the aromaticity. And the way we do that is you're going to have some base around, and it's usually some conjugate base. It's not like you're adding sodium hydroxide to the reaction or anything like that. So some kind of base that's in solution is going to grab that proton, pushing the electrons back into the ring and restoring the aromaticity of the system. And so the final product is simply going to be benzene that has one of its hydrogens substituted by your electrophile. And that's the easy part of the reaction. Because you're taking that very high energy sigma complex and making it aromatic again. So all of these EAS mechanisms are going to be two-step processes. The first, the pi electrons attack the electrophile. In the second step, you restore the aromaticity of the ring. Okay? Yeah.
Is the energy of the first one lower than the energy of the second?
It just depends. It depends on what specifically you're adding to the ring. But they're going to be relatively close in energy. Okay, does that generalized mechanism make sense? Any questions on that?
What does the B represent?
The E, or, oh, the B? The B represents some base,
Oh.
and it's usually some conjugate base, related to what it is you added to make the electrophile. Okay, so we'll see some specific examples.
Its purpose is just to move the H down to the cation?
Yeah, so it's just going to act as a base, so it's just going to abstract that proton, and as it pulls that proton, the electrons of that bond get pushed into the ring to quench the carbocation.
Is there any like real world application of this?
Any real world application?
Yeah.
Oh yeah. Because if you want to put anything on the benzene ring, like well, an example we're going to see in just a second. If you want to add benzene rings to a molecule, for instance, which you want to do all the time because benzene rings are found in almost everything, you've got to functionalize this, because you think about, well, how can I add a benzene ring to a molecule? Well, you've got to have something that can do a chemical reaction. And one of the most common ways of adding benzene rings to molecules is through Grignard chemistry. Well, if I'm going to do Grignard chemistry with a benzene ring, I either need to have a halogen on here, or I need to have a carbonyl on here. So you have to be able, if you want to put benzene rings into things, you have to have a way of functionalizing the rings to make them do chemical reactions. And so that's what this EAS mechanism is so useful for. It allows us to functionalize the benzene ring so that we can do chemistry with it. Okay? So that's a good segue into our first reaction, actually. So let's look at a specific reaction we could do. One of the most common things you're going to be doing with these is halogenation. So putting halogens on the benzene. And just like you probably noticed a trend when we were dealing with the halogens, typically we're only going to be dealing with chlorine, bromine, iodine. If you mix benzene with fluorine, it tends to explode, so we're not gonna do that. But we're gonna take benzene, and you're gonna add whatever molecular halogen you want to appear on the ring. So let's say bromine. But I already told you when we started this discussion, you're not going to be able just to put benzene and bromine together and expect a reaction, because bromine by itself is just not strong enough electrified. So we're going to have to do something to really amp the electrophilicity of the bromine. And what we do is we typically add a Lewis acid. Aluminum bromide is a common one. Iron bromide is a common one. Some kind of a Lewis acid. And we'll go through the mechanism of this in just a second. But ultimately what that will do is allow you to put the bromide on the ring. So let's go ahead and look, what I want to look at first is, what is the purpose of the Lewis acid? Like, why is it that it converts the Br2 into such a strong electrifier? So if you consider those two things, the molecular halogen and the AlBr3. Well, the first thing is, what's the definition of a Lewis acid? You know, I mean, we typically deal with the Bronsted-Lowry definition of acids and bases. Now we're dealing with the Lewis definition. Anybody remember what that was? Close. The Lewis acid is a lone pair acceptors. Okay? So this is looking for lone pair electrons. Well, you just happen to have a whole bunch of those on the bromine.
You said it's a lone pair acceptor?
Yeah, or lone pair acceptor. So the way I tend to envision this reaction happening, probably not exactly true, but it makes it simpler for the mechanism, and so that's the way I'm going to draw this, is the Lewis acid is looking for electrons. And so one of these bromide lone pairs is going to go in and jump onto the aluminum. And if that happens, what you end up with is aluminum with an extra bromine, so it's going to now be AlBr4, and it's going to have a negative charge because the bromide attacked it. And then what's left is more important. What you're left with, if you lose Br minus from Br2, what you're left with is Br plus. So if you think about that for a minute, halogens are very electronegative atoms in general. They're way far on the right-hand side of the periodic table. So how happy do you think a halogen is going to be bearing a positive charge?
Not happy.
Not happy at all. So that is your super potent electrophile. It is going to grab electron density wherever it can get it, because halogens, being as electronegative as they are, do not handle positive charges well. And so, once you have that form, the mechanism is really simple. The electrons are going to go out of the ring, attack that. Let's go down here with this. That should make that high energy sigma complex. And then in the next step, it's going to be that AlBr4 minus that comes in to act as the base. So it's gonna come in, grab that proton, electrons come down, and ultimately result in your substituted benzene. And by the way, just to kind of keep track of our atoms here, what that also results in is the H AlBr4. Well, that's very, very unstable. It decomposes almost immediately, and it decomposes to HBr and AlBr3. And the reason I put that in is because that step regenerates your catalyst. Okay. Any questions on this mechanism that we just covered? Okay, so I want to go and just kind of show you some of the reaction conditions here. So to show what else, what other halogens we can use, and what reaction conditions we would use to put them on. All right. So I'm going to just make a little table here. So what atoms we can put on, and then what conditions we use to get that atom on. So we could put a chlorine on the ring, and we would use very, very similar conditions to the bromination. You could use Cl2, and generally what you'll note is we're going to match the halogens on the Lewis acid to whatever you're trying to put on the ring. So before we were trying to put bromine on the ring, so we used iron bromide and aluminum bromide. Here we're trying to put chlorine on the ring, so we're going to use iron chloride and aluminum chloride. So we already looked at how to brominate. Very analogous conditions. And finally, we can also put iodine on the ring. These are slightly different conditions. You typically use molecular iodine and then some oxidizing agent. So peroxide sometimes is used, copper salt. Even nitric acid is sometimes used. Okay. And so getting into the question that was asked a minute ago, why do we even care about doing this? Why would this even be useful to us? What you're probably going to be using this for quite extensively is in the context of Grignard reactions. So if I wanted to put, say, an alkyl chain on my benzene, you're going to need to have some sort of a halogen on the benzene in order to do a Grignard reaction. So add the magnesium, throw in some carbonyl, whatever it is you're trying to put on the ring. And work up an acid. And if you recall, mechanistically the way this works is the addition of the magnesium causes the wherever the halogen is to essentially become a carbanion. So it makes the carbon-based species into a carbanion nucleophile, which is then going to go and attack the carbonyl. And so upon workup, what we would get is the benzene ring now that has that 3-carbon group on it. So that's the primary use of these halogenation reactions on the benzene. They allow us to make Grignard reagents, which allow us to incorporate the benzene rings into molecules. Okay. Any questions on that? Okay, I think that's probably a good place to stop for today. So I will see y'all in the lab in about 10 minutes.